So in the simulation, you just saw that you can convert forms of energy into other forms. The ones that were shown were mechanical. You'd see the person riding a bike, moving something. You could see electrical traveling down the wires. You could see thermal as different things were heating. And you could see light. You saw that the electrical energy ended up heating the filament in the light bulb, which then converted into light. And you also saw that chemical energy is something that happens in our bodies. It happens in all over the world, all around us. There are several more types of energy than just these ones listed. These are just some examples to get you thinking around the idea of energy not being lost, but it being converted into other things. You may want to read through this chemistry scenario focusing on energy conversion. So when gasoline is combusted, that's a chemical reaction. Within the cylinders of a car engine, it produces gaseous carbon dioxide, and then the rapidly expanding carbon dioxide pushes against and moves the pistons in the car cylinder, which is mechanical energy. And then when the vehicle battery, which is chemical reaction, is connected, it produces electricity carried to other systems. So you can just see we've got a lot of energy conversion going on, but it has some chemistry in there too. Here's a great big reminder. This symbol, delta, means change. So if you have a delta T, that means a change in temperature. It's your final with an F minus your initial with an I. You can also have a change in volume, which again is final volume minus initial volume. Now, if you have another section of notes that doesn't have this in there, I have updated it. I realized I oversimplified, and I wanted to make sure that we were very clear. So work is only going to really be discussed right here within this chapter. It does come back in Gen Chem 2. It also comes back in the gases chapter. So work is the process of causing matter to move against an opposing force. So like in the example of the car engine, it was creating a gas, and that gas was expanding, and gases are so very strong when they expand. It's moving that cylinder upwards, that piston upwards. So here's what you have to think about in Gen Chem 1 though. The entire system is an open vessel, even including our coffee cup calorimeter, which you'll hear about soon, but it's just a coffee cup that has a reaction going in it, and then you have one of those little coffee lids that are really loose on top. So earlier you saw delta U, but in these systems, we define something new. You'll see it in the next series of videos quite a bit. Delta H is very useful information for us. Rather than worrying about the internal systems energy, we define H so that our Q at constant pressure, it is at constant pressure because if you start a reaction at, like in your room at 1 atm, like it's still 1 atm when the reaction finishes. You know, the pressure isn't changing. So we're defining delta H as Q at constant pressure. In Gen Chem 2, you're going to encounter other systems where work will be included when we do energy calculations. You'll see expansion is negative W and compression is positive W. Again, we are only going to be focusing on delta H and figuring out delta H from Q at constant pressure. Then there's another condition that you can also have that we only bring up one time, and it's constant volume. And we do mention a bomb calorimeter. This to me, it kind of reminds me as like an old-fashioned canning system kind of thing where you can lock it down so tight and put tons of pressure and heat in the thing, and it's not going to blow up on you in theory. So a bomb calorimeter is like that. It's like these little really thick metal walled containers that screw very tightly into each other, where the lid connects very tightly to the container. And sometimes they even have clamps to help hold them together. Sometimes they don't. Sometimes they have things coming out of them. You can Google and look up bomb calorimeters if you're curious about them, but they hold pressure very tightly and they don't pop open. So we will mention a bomb calorimeter just very, very briefly. It's the only system in Gen Chem 1 where the pressure is not constant and your volume is not going to change in that system. So notice if your volume doesn't change, your pressure times your volume doesn't change, your work is zero. So for those kinds of systems, your energy is also called Q, but this Q is at constant volume. The other one was constant pressure. Again, for the test, you do not have to know this. This is just a little bit of extra for people who want a little extra and who may be confused at why there's a Q in some places and a Q in other places. We use little subscripts to help us know which Q we're talking about. For the rest of the chapter, we are talking about this Q here. Also, one little note too, on state functions, they don't depend on path by which a system reaches its current state. So state functions in the chapter, here are some words. These are state functions. Up here, when I was talking about Q at constant pressure, or this at constant volume, that's a path function, not a state function. Again, this is just a little bit of extra. This whole little section I'm commenting on, it's a little bit of extra info. So a state function is where, let's say that you have a budget, and let's say that you're one of those people that doesn't have a credit card and you only have the money for your budget and you're really strict about it. So let's say your budget is $500 for incidentals or your rent and whatever else. If you spend all $500 on the first day of the month, you end up with zero. Or you could spend your $500 over the course of several things throughout the month. And then finally, at some point, you'll end up having spent all of it. It's a state function because it doesn't matter whether it happened all at once or whether it happened throughout the month. In both cases, the final at the end of the month minus the initial gives you zero.